All right, welcome to the instructional part of the course. We're going to be covering Chapter 1 first. Chapter 1 is an overview of what computer programming is about and the different levels of computer programming, and also a few bits and pieces as well as some information about Alan Turing. Not a whole lot of questions on your exam about this information, but there are a few, and I'll discuss those as we go through. Now, this idea of computing is that there's, no magic to it. You just have to think of everything, single step, and think about it in a methodical way, and it has to be very procedural. So you give the computer the step-by-step instruction on what you want it to do, and then it's going to do that same thing every time. It doesn't make a decision to do something else unless you ask it, hey, if this, then this, and then it makes a determination. But it will work it that way every single time. So we're going to build our understanding from the bottom up. The author first goes through Chapter 1, which we have our overview, and then Chapter 2, we're going to talk about bits and binary numbers and representations of different data types. Chapter 3, we're going to go into the logic gates, and then also talk about what transistors make up these different gates and how those are accomplished. And then we will start programming in chapters 4 and 5, and chapters 6 through 10 we kick it off and really have a good time. Two recurring themes here is you can drive a car and not know how your engine works, and everything goes fine until something doesn't. And then what do? You got to call somebody, or if you have to fix it, what are you going to do? So for computer programming, it's important that you know how both the hardware and the programming, how they work together. So we're not just diving in straight to a high-level programming, which a lot of people do. We are going to start from the very bottom. We're going to start from the wires and the transistors, both the hardware and the software. The hardware, that's going to be like the physical components and all of those attachments, whether that be the mouse, the monitor, that's all hardware. The case, the actual bits and pieces that make it up, the transistors, the microprocessor. Now the software, those are the programs that you are going to be using. Those, whether that be Windows, Excel, any of your apps, your database systems, Fortran, Basic, whatever it is that you're programming in C+. So even if you specialize in one, what the author is wanting you to do is have a good knowledge base of both, and that's what we're going to attempt to do in this class. So looking at a few computers in the 1940s, computers which they weren't capable much at all, but they would take up entire rooms. Then in the 80s, we had more powerful computers, of course, than in the 1940s, and now our smartphone, which something that used to take up an entire room, entire floor of an office building, now can be done with just a smartphone. So we have a few little history of microprocessors. A microprocessor is, a little less than an inch squared. And something that is just crazy is it contains many millions of transistors. So this is our thinking part of our computer. We have 3 different parts of our computer. We have our computing part. This is the brain. We've got the data storage, which is our memory. And then, of course, we have all of the pieces that go along with that, such as your keyboard and your mouse and monitor, whatnot after there. All right. So the big idea was we needed this universal computing device. And Alan Turing is the one who thought of this. With our computers that we have, given enough time and memory, they're all capable of doing exactly the same thing. But some of them have more memory, some of them are souped up, Maseratis, and others are, just a basic Honda. But they still get you from point A to point B. Some of them do it a little faster, some of them do it with a little more flash, but you're still doing the same thing, going from one point to another. Anything that can be computed by a computer, and I don't care which one it is. So we just need enough time and memory. When I first started graduate school, I had a computer back in the late 90s, and I would get it set up to work, and it would take all night long to think through programs that I had written for it. Now, it wouldn't take it but just a few moments. All right, here's Mr. Turing. In 1937, he came up with this idea. Now, he didn't really ever build one. It was just his idea that if we had this, if we could write something on an infinite tape and we could come up with different symbols and a computation, we could have a machine that could do our computing for us. So given two inputs, A and B, I could have a machine that would come up with A plus B. Now, whether that meant that it just took and, A plus B, it took however many sticks and it counted the number of sticks, or if we were talking about multiplication and I wanted to do A times B, I wouldn't have to know multiplication. I could just do multiplication with series of addition. So I just put some adding machines together and I could get multiplication. So any machine that you can put together of all these different Turing machines is going to be our universal Turing machine. And here we have a multiplying Turing machine which uses an addition Turing machine, and then you put that together with more inputs, and then we could have something that did a multiplication times an addition. This would mean that our U is a computer, and you will be programming with ones and zeros with a set of instructions, and you will be able to add. And so you're creating, in effect, this universal Turing machine or a computer. These 7 layers of transformation, you will need to know what they are for your exam. So be sure when you're asked on exam, what are the 7 layers of transformation? Now, I might have a whole lot of words there and you just select them. I won't have you memorize them, but I might have you put them in order. So there are problems, there are algorithms, there's a language that you must speak, there's the ISA, which is the instruction set architecture, there's the microarchitecture circuits. Our devices would be the final one on that. First up, our problem must be in the form of a clear statement. So here's your first quiz question. Get out your pencil and write this down. The chicken is ready to eat. So for your quiz, what you will write down is you'll write quiz 1, and this is question 1. The chicken is ready to eat. This is not a clear statement. It's an ambiguous statement. And by giving 2 interpretations, what that means, you might call them A and B. I'll go ahead and work this one with you. The 2 interpretations might be A, the chicken, meaning a physical chicken out in the yard that is walking around, he's ready for you to come feed him, so he is ready to eat. B, another interpretation might be the chicken that I've prepared in the oven for my family is now ready to eat. That would be another interpretation. So on your piece of paper, write down 2 interpretations of this statement, which I gave you my 2. If you have something else, you write that down too. So our problem must be in the form of a clear statement. If I asked you to write the sum of the first, let's say, 3 integers, you could do that. Sum of the first 3 integers beginning at 0. Let's say you would go, oh, I just need to add 0 plus 1 plus 2. Those are the first 3 integers. And you would say that the sum of the first 3 integers starting at 0 would be equal to 3. Or I could say the sum of the first 3 integers starting with 1, and you say, oh, that's 1 plus 2 plus 3. It's very clear. You know what you're supposed to do. The algorithm is the step-by-step procedure that you follow. And this would be like a recipe if you're solving an equation or if you're going to multiply what it is that you do, or alphabetizing. The third step, or the third transformation for a computer, is actually writing this step-by-step procedure into a programming language. And we got more than 1,000 to choose from. Fortran, Basic, C++, Assembly, and machine language, which we're going to do C++, Assembly, and machine language. So we'll know 3 of those when we're finished with this class. Now, the fourth level of transformation is the ISA, and that's the set of instructions the computer can carry out. For the LC3, we have 20 instructions. Here are our 20 different instructions that we will be programming. Our LC3 stands for Little Computer 3 because it's the 3rd generation. Here are 20 instructions that we can give our little computer. And you'll be surprised at what we're going to make this little computer do with just these types of add instructions. There are logical operators, these 2 ands and a not, this branch and jump, these jumps, these and the return. They can move from one line to the other depending on certain circumstances. These are loads, these are and stores. These are part of the memory and how we're going to move around within our program. So we just did the instruction set, so let's look at the microarchitecture. What that actually does is it transforms your instructions into implementation. It makes it roll throughout. It moves the circuitry, moves the voltage through our circuits. And then our circuits are these logic circuits that we use, whatever these transistors and happen to be, or microprocessors, and our devices, the particular type of transistors that we use. Now we're on to chapter 2 of our instruction. So how are we going to represent this data in a computer? How we're going to do this is with the flow of electrons. Now we're going to have 2 conditions. We either have voltage or we don't. And we're just going to call, if it has voltage, we're just going to call that a 1. If we don't have voltage, we're just going to call that a 2. And we could base the state on the value of the voltage, but we don't really care how much voltage. We just want to say, well, we do care how much voltage. Because within a certain range, that's going to be a 1. And then if it's a really tiny amount of voltage or 0 voltage, we're going to call that a 0. And they say compare it to sticking your finger in a light socket, or even just talking about in your house. You know, your house has 120 volts in your socket. You don't really care if it's 118 or 122, but you do care if it is 15, because that's not going to run what you're asking it to run in your house. We have 2 different types of signals. We have analog, which are the continuous type of signals, and those just roll all the way through in time. Discrete is a sampling at specific times, and we could get our discrete signals, we could get it more accurate by just increasing our sampling. So here we sampled at, let's see, we sampled at a half, and then we sampled here at 1.5 and at 2.5. We could just do it on every single half, and then that give us an even better idea. But discrete will get us the general idea of the shape provided we sampled enough. So computer is like this digital system. It's not continuous. It is just telling us on, off, or yes, no, or true, false. And here is the amount of voltage that makes up our ones and zeros. If we have a voltage that's between 0 and 0.4, we're just going to call it a 0. If we have a voltage that's between 0.8 and 1.2, we're calling that a 1. Anything in between, that's no man's land. I don't know what the little logic gate is going to consider that. It could consider it a 1, it might consider it a 0. That is going to be called noise. That's going to be something that I really have no idea what it's going to do. In chapter 3, we're going to see how these logic gates work in order to give us our zeros and our ones. And we're going to try to make sure that we don't have anything that happens in between there in the no man's land. So each wire is either going to be a 1 or a 0. So for each wire, and the wire is just one single 1 or 0. So if I have 2 wires, or we're just going to call those bits, so if I have 2 wires, I can get 4 different values, because if my first wire has no voltage, we're going to call that a 0 in total, and that's going to represent maybe a 1 to us. Then if I have no voltage, and then on the second wire I have a 1, we're going to call that a 1. We have to be able to think in terms of how our human brain thinks, because we don't think in terms of 1s and 0s. If we have a voltage on the first bit and none on the second bit, we're going to call that a 2. If we have voltage on both, we're going to call that a 3. What happens if I have 3 wires? Well, with 3 wires, I can represent 8 different values. So here I have them uniquely listed out and how I'm going to represent what is happening on each of those different wires. So you will notice that with however many wires that I have, so if I had 4 wires, that would mean that I would have 2 to the 4th, which would be 16 different possibilities. And let's also notice that with 2 bits, I can represent the numbers 0 to 3 because there are 4 values. This makes it a little tricky because it's 4 values, but because we have a 0, the numbers range from 0 to 3. If I have 3 bits, then the numbers, because there's 8 different possible values, the numbers will range from 0 to 7. Here's your question, quiz question, get out your piece of paper. With 5 bits, how many different values can be represented? Well, with 5 bits, let's see, that means I will take 2 and raise it to the 5th power, and 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 again is, that answer would be 32. Be sure and include a little bit of work that I went through with you. So what kind of values do we want to represent? Well, with our computer, we want to represent numbers, whether that be integers, fractions, real numbers, complex or imaginary numbers. I want to represent text on the screen that we're looking at. Images, I want pictures. Everybody loves the pictures on the computer. Sound and video, I want those because I have to stream my video. I also want logical, true, false kind of statements, and then I also want my instructions of what the computer is going to be doing to be represented. So all the data is just a collection of bits, which are these little wires that either have a 1 or a 0 on them. and we're going to encode that with either a 0 or a 1, and then that ordering is going to matter to us. So with our data type, these different representations and operations, we can either have unsigned integers, which is just binary. That's just 0, 1, 2, 3, 4, 5, 6, 7. And then we can have signed integers. Now, that we're going to represent with 2's complement, but it's going to take us a little bit to get there, but we will get to it in this particular video. Real numbers, we'll do that one in the next video, and the 2's complement, we'll do some in the second video too. And then the ASCII, we may touch on that in this. No, we'll do that in the next one. Unsigned binary numbers. Okay, here we go. So I could say that the number 5 is represented with a string of 1s. And remember, I've only got 0 and 1s to represent this with. Oh, there's a problem with that. What I've decided to do, because I just can't just randomly go, oh, just all these 1s are a 5, because I can't manipulate it with that. So what I'm going to need to do is I'm going to have to do weighted positional binary notation, just like our base 10 numbers. The number 329, that's 300, 300ths, and that's 2 10s and 9 1s. So that's weighted depending on the position of where that 3 or that 2 or that 9 is. We do the exact same thing with our binary. So here is what our base 10 system looks like. Let's compare it to what our binary numbers are going to look like. So position, the 0 position, 2 to the 0 position, 2 to the first position, 2 to the second position. And we'll continue that on. The next one would be 2 to the third. Just like if I was working with these 10s, the one up here would be 2 to the third, which would be the thousandths position. This first position here is called the ones position. This next position is called the twos position. The next position is called the fours position. The 2 to the third would be considered the eights position. And if you will notice, I have 1 4, no 2s, and 1 1, and that would add up to a 5. Here I have listed each of these positions. So this is the 1s, this is the 2s, this is the 4s position. Let's go to these 5, this decimal number 5. I have 1 4 and 1 1, and that equals 5. Notice I'm adding them all the way across. The 6 as a decimal, that's 1 4, 1 2, no 1s, and that would be a 6. And this is just rewriting it horizontally. Notice that if I have n bits, so in this case I have 1, 2, 3 bits, I have 2 to the n minus 1 numbers that I can represent. So 3 bits, that's 8 numbers that I can represent, and it ranges from 0 to 7. I can also do fractions. Isn't this crazy? 2 to the negative 1. Remember that a negative exponent means 1 over. So this is 1 over 2 to the first. This next one is 1 over 2 to the second, 1 over 2 to the 8th. I'm not going to go further than this on exams with you. This is just so that we will understand how this works. And on exam, yes, you will have to manipulate a fractional part in binary. All right, if I have 3 of these bits and they're in the fractional part, in this 2 to the negative third position, I have 1 of those. If I have 1 of these 2 to the negative 2, then I would have 0.25. The next one is if I have 1 of the 1/4 and 1 of the 1/8, and I would add those together. And if I want more decimal points or I want more accuracy, I just add more bits in the fractional part. Here I have a chart for you that is written out in binary, 2 to the first, what 2 to the first, what 2 to the second, 2 to the third, 2 to the fourth. You'll become very familiar with all these powers of 2 by the end of the next 2 chapters. So each position has a place value. Same thing with your binary numbers. Same thing with your binary numbers. So let's look at example 1. And it's a 5-bit unsigned binary number. Here we go. Let's count my bits. Yeah, I have 5 bits. I usually start at this 0 position, so I usually start a little backwards. So I have 1 in this 2 to the 0 position. I have nothing in the 2 to the first position. I have a 1 in the 2 to the second. I have a 1 in the 2 to the third. And then I have a 1 in the 2 to the fourth position. So let's look at what that would be. I just go ahead and write in what each of those is. So that means I have 116, 1-8, 1-4, none of those in one of those ones positions. I can just add all of those up, and I can now say that 11101 in base 2 is equal to 29 in base 10. All right, let's play again. Like I said, I like to count them backwards. It's easier for me. So I'll start here at this back end position here. This is in base 2. And I have one of these ones, none of those 2 to the first, one of those 2 to the second, one of those 2 to the third. Write down exactly what I have. And then I'm going to add up the 8, the 4, and the 1. And I can tell you that 1101 is 13 in base 10. Let's play it again, and let's do a fraction. So this time I'm just going to write down what I have. So I don't need to go through all of those to make a point. And I can see that I have 1 in this 2 to the second position, 1 in this 1 position. So that makes my 5 in my fraction. I don't have a 0.5. I have a 0.25. And I have one of these 0.125s. All right. So what you are going to do is get out your piece of paper, and you are going to have question 3. 1011.1011. Give me the decimal number that is equivalent to this binary. I've gone ahead and marked this up for you. I'll give you a few minutes. All right, the answer that I got for this was 11.6875. And hopefully you did too. Be sure and show that work on your quiz. And this will be the end of this part 1 of our lecture. All right, I know you're looking forward to part 2.